Hello everyone, I am Mansoorally, and I'm going to be starting us off with the easy sum. The easy sum uses modular arithmetics to avoid working with large numbers directly. It starts off with an input that includes t, the number of test cases, n, the last number in a range, and m, the constant divisor. Well, what does this all mean? Let me show you with a simple example, where the first value here tells us that there are two test cases. To take all the numbers from 1 to n, which is 10 here, and for each number divided by m and find what's left. This is called the remainder. And have all the remainders and do this for both the test cases. And for this input, we will find that the output is 20 and 10.
Next, let's discuss problem number 2. Before we proceed with the calculation, let's understand what the flow function does. It basically rounds off a value to the nearest integer that is less than or equal to the value. We will be given an array with n amount of numbers within the given constraints. We have to identify each and every unique pair of the numbers in the array. After identifying the pairs using this equation, we have to calculate the flow value of every pair and include them in a set. The addition of every number in this set is the answer. Let's discuss this with an example. For an example, let's consider an array of A with numbers 1 for 1. So first we have to identify each and every unique pair, which is shown here in the document. And after substituting these values to the equation that is provided to us, we have to calculate the flow value of all the three pairs. And these values should be added to a set which will be named by anything you like. And then finally, to get the answer, you have to add up all the numbers in this set.
Next, let's discuss problem number 3. We are given the equation method in step 1 and the answer will be the last two digits of S. K and N are two variables that will be given to us. The first line of the input will be the number of test case and the line after will represent value of K and N respectively. The value will progress as shown in step 5. If we consider this numerical example, you can see that we have three last cases as shown here. We have to calculate the S value of each case by substitute value of the equation in step 1. Accordingly, the input will be last two digits of Sn for each case. This value should be printed separately.
First, we start with input values. The input consists of three numbers. C, the first term of the sequence. M is the modulus. And N is the number of 2D vectors. Step 1 is to generate the sequence using the formula given. We calculate up to A to n plus 1. Step 2 is to group these values into 2D vectors. For example, V1 equal A2, A3, V2 equal A4, A5, and so on. Step 3 is to compute scalar products of all unique pairs of vectors using the formula x1 dot x2 plus y1 dot y2. These products are stored in a set to ensure uniqueness. Step 4 is to take remainder of each scalar product modulo m and store these remainders in another set. Step 5 is to count the number of unique remainders and find the remainder of the count of modulo m. This gives the final output. For example, with input 4, 5, and 3, we calculate three vectors, compute their scalar products, and find the final output is 2. First,
Hi, let's quickly understand summoning the Kane series. Sin equals T1 plus T2 plus T3 plus Tn. Each term Tn equals K, where n is the term number, K is the power. Example, K equals 0. Each term, every term is 1. So Sn equals 2. K equals 1. Term are 1, 2, 3. And Sn equals 1 plus 2 plus n. For K greater than 1, compute powers, sum them. Example, for n equals 3, K equals 2. T1 equals 1, T2 equals 4, T3 equals 9. Therefore, S3 equals 14. For large sums, use module 10 to the power 9 plus 7 to simplify. Follow this step, calculate Tn sum, and apply modular if needed.
Hello everyone, let me explain problem 6, fun with series.
We calculate a sequence G using the formula Gn equal A sub Gn-1 plus B sub Gn-2. G0 is 0 and G1 is 1 are given. Then we find the certain C where the sum equals 0. According to this, 2C0 plus C1 plus C2 equal to 0. Then using this we calculate S value. According to the equation, SP equals sigma Ci mod 10 to the power 9 plus 7. Finally, compute the product pi Ci and substitute value to get the final result. In this example, the output is 0 to 0.
Imagine you have n children sitting in a circle, each with an initial number. They play a game for m rounds where each child's number is influenced by their own value and the values of their left and right neighbors. To model this, we use a transformation matrix where each child contributes to their value. Their left neighbor contributes, their right neighbor contributes. The matrix is applied repeatedly for m rounds using the matrix exponentiation to compute, which gives the cumulative influence after m rounds. The final result for each child is calculated by multiplying with the initial numbers and taking modulo. For example, starting with 1, 2, 3, 4 and applying this process for 3 rounds results in 58, 58, 62.
Hi everyone, let me explain problem 8 counting summation. We are working with the 2 by 2 matrix A, where A sub 1 to 1 equals 0 is fixed and other elements A sub 1 to 2, A sub 2 to 1 and A sub 2 to 2 can be either 0 or 1. So there are 8 possible configurations of the matrix. Each configuration is analyzed to find its rank. The rank determines how many unique equations the matrix represents. Based on the rank R, the number of solutions to the system is calculated using the formula P to the power of n minus R. For example, if the rank is 0, there are 4 solutions. If the rank is 1, there are 2 solutions. None of the configurations here result in 0 solutions, which is interesting outcome. The goal is count how many configurations give exactly 0 solutions. But here none do. This process applies to similar problems. To understanding this logic is key.
I'm going to explain the ninth problem, which is XOR love. So this problem is based on XOR operation. So this is our formula. And this task involves a list A containing integers from 1 to n and queries that specify 3 values K, P, and R. This defines a range of elements in the list AP to AR. For each query, we calculate a sum called KPR sum by examining all unique pairs of elements in the range. For each pair, we calculate 2 things: XOR of the 2 elements, XOR of the result with K. Finally, we sum these values across all pairs in the range. For example, if n is equals to 3 and the query is K equals to 1, P equals to 1, R equals to 3, we calculate XOR values for the pairs 1, 2, 1, 3, and 2, 3. Adding them up gives the result of the query. This problem tests your ability to work with XOR operations and nested loop efficiently.
Finally, we'll be discussing problem number 10. Here we have to take the sum of a series up to infinity. For this, we have to decompose the series into partial fractions and solve the coefficients. Then we can rewrite the series by substituting the solved values for the coefficients and observe that the consecutive values cancel out, leaving only the first and last terms. Finally, we can apply the limit and calculate the sum, and this will be the answer. For an example, we can take this general term and decompose into partial fractions. By solving it, A will equal to 1 and B will equal to minus 1. By substituting values for the nth term with the summation, we can see that each consecutive term gets cancelled until infinity. And finally, we will be left with this term. By applying limits, when n approaches infinity, we can see that 1 over n plus 1 approaches 0. Therefore, the series approaches 1 and we will get the answer.